I thought it would be appropriate to review a little bit of what I've done over a period of years on blue waters. Over this last year, since the end of August, I've been off of blue waters, and I'm anticipating being on Frontera. And so I've had some time to develop some new things. Make my code do some new things, and I'll tell you about that. That's somewhat technical. I'll just show this one. I thought I wouldn't show this slide, but I'll just show this slide to explain that all of the work that I'm doing in simulation is on Cartesian grids, and this is just to indicate that Cartesian grids are just wonderful, and that whatever you thought was wrong with them is not wrong with them. Okay, so I'll say no more about that. And so I want to describe a little bit what I have been trying to do. I've been working with a team of Falk Herwig at the University of Victoria in British Columbia, and we are looking at the interiors of stars. And this picture may not look very much like a star to you, but what we are looking at are phenomena that depend critically upon what happens just at the edge of a convective zone in a star. And so this is showing a zoom in on the top of a convection zone, and the colors which have been enhanced, if you could see it and you wouldn't burn up, it wouldn't look like that, but we tried to make it pretty to show how at the top of the convection zone there is fluid above that is stably stratified. And according to theory and a typical one-dimensional model for stellar evolution, none of that fluid would ever get incorporated into the convection zone. And this is just showing that indeed it does get incorporated. And we've been looking at phenomena that depend upon precisely how that happens. It's a small-scale phenomenon that goes on at the top of this convection zone. And you might think that we would really need to zoom in the grid and have an adaptive grid to pick that up. We don't do that. What we do instead is we try to do just a very loving description of what is going on there and build a lot of accuracy and detail into the treatment. And I'll be telling you about that a little bit. This is a slide from Falk Herwig that just is showing the thermal pulses as a function of time going along the x-axis, and then a mass coordinate in a 1D stellar model going along the vertical axis, showing you that at intervals in the final phase of evolution of a low-mass star, you have these helium shell flashes that occur because helium and hydrogen are not burned at equal rates. And so the helium ignites suddenly, sets up a convection zone, which you can see as the shaded region, and the convection zone grows over a period of, maybe a couple of years. And it can grow up to the point where it reaches fluid that has hydrogen in it, and it can pull that hydrogen down, and that produces something called the hydrogen ingestion flash. And that it's good to be, if you're doing things in 3D, you want something to happen fast enough. And the helium shell flash sounds like that ought to be fast, but 2 years, that hydrogen ingestion flash is 2 days, and sort of now we're talking. This is just a diagram to show that if you don't look in the mass coordinate, but if you look in the radius, you can get a different picture of this. This is that convection zone above the helium burning shell, showing how it expands and it lifts all of that stuff that's up above it upward, which is what turns off the hydrogen burning. And those are dashed and dotted lines that are Lagrangian lines, showing that it really is moving into some more of the stuff and can pull it down. And the way that it pulls it down is through these very complicated things that go on at the edge. And we've been looking at that on blue waters. And this is another one of these sort of time on the x-axis and mass coordinate on the right axis, and it would take me too long. I can see from the clock, there's no time to explain what this means, but you should just see that, well, it's sort of a mess. And this is what we're planning to study with the enhanced code. If we look at it in space, this is an early sort of test shot at this. The idea is that we're going to go from one convection zone to two convection zones, and expand our grid and do some more stuff. And this is a situation that can occur for massive stars, where you have a number of burning shells as you go out, and above each one there can be one of these convection zones. And in between them, there are just these little slivers of mass, which according to the analytic criterion are completely stable and should just be sitting there beautifully. And I remember in the 1970s that Iko Eben came to the Livermore lab where I was working at the time, and he showed us something like this, not this kind of picture, but a massive star with these convection zones, and in between them this just sliver of stuff, and just said, what should I do? Does this eat through? Does it not? I'm completely at a loss. And he thought that since we could do things in 3D, we could just solve that problem. And well, we could, those of us who are still alive. And the plan is, well, to do it, and I thought I would have it solved. I mean, I was supposed to start April 1st, but they kept sending me a note, well, how about May 1st? And thought, I can do a much better job on my code. Well, what about June 1st? Well, I could do, and now it's June 17th. Well, wow, I can. So anyway, I was inspired by someone else's talk that they had these why blue water slides, and of course I haven't used the template and I haven't obeyed any of the rules, but then I haven't computed on blue water, so for the last 9 months. But I like this idea, why blue waters? And so I thought I would show you what was cool about blue waters to me, and we'll see if this works. Okay, so this is a movie of my first calculation on blue waters in 2012. And it had 1.17 trillion grid cells. And Mike has now done 2 trillion grid cells. But this was, I thought it was really pretty cool. We made a lot of effort to get over 1 trillion. And we had to fill up the machine and all kinds of things. This is dump 27. And, I'm just at the process now where I have had to promise to the NCSA people that I will delete this run, which has been kept on their file system for all these years. And so we can sort of bid it adieu. It has served its purpose. Results from it were shown at DOE headquarters and apparently caused somewhat of a stir. I wasn't there. I'm probably glad I wasn't. But anyway, you've seen that with 1 trillion grid cells, there's lots of detail. There's so much detail that one really needs a bigger screen. And of course, this is only one panel out of a multi-panel screen of this thing. I'm sorry, it's what I had on my laptop. So that's what I did in around Christmas time, 2012. and it was absolutely wonderful. And then what we did after that was to model these stars. And here's a picture of one of them. We made a movie out of this run, which was done, well, we did it in 2013, and then we did it again in 2014. And it sort of goes too fast. It's the only one that I happen to have on my laptop when I decided I should show these old movies. We made it go really fast because we hoped that Irene Qualters would show it to the National Science Board, and we tried to get the time down. If we could play it at a faster frame rate, maybe she would show it. And so, well, what is it? Well, it's almost finished now. But what it is we've sliced this star in half, and we're looking through it. And what you are seeing at the beginning is the top of the convection zone. And I'll let it play again because it's really quite a short movie. You see the top of the convection zone looking from the interior of the star up. And you see the material that is visible is the hydrogen-rich material that is being brought in by the action of the convection. The material is actually stably stratified, so in principle it's not supposed to come in, but it doesn't know that, and so it does, because after all, you have this turbulent convection going on beneath it, and these things are gases, and so of course it is brought down. What you can see is a representation of the nuclear flame that results. This hydrogen-rich material normally would not find itself in this part of the star where it's much hotter and where the rate of burning goes up very, very rapidly as a high power of the temperature. And so as this gets going just about now, it self-organizes in such a way that we have sort of a ring of nuclear flame that goes back and forth. You can see it going back and forth from one side of the star to the other. And what that does is it pulls down much more of this material than would otherwise come. It increases the ingestion rate by about 2 orders of magnitude. And so one forms this layer that looks sort of like the edge of a cantaloupe or something like that. That's a hydrogen-rich layer, which then feeds the next round of this thing, and then it sort of explodes, except we don't let this star explode because it's held in with a spherical boundary condition, and so we stopped the calculation at that point. So that's what we did on Blue Waters up through about 2017. And I told you last year what we did in 2018. And what we want to do next is to solve that problem that Eben posed. Can we eat our way through one of these very thin layers and eat into the next burning shell? And we've done some studies in 1D that suggest that, gee, if we could do that, wonderful things would happen. And there would be nucleosynthesis that would be enabled that would not otherwise. And, well, my friend Falk seems to think that that could solve the abundance problems for certain isotopes, the odd Z elements like potassium, chlorine, and some other less well-known elements. So what I had done was I was going to prepare and tell you all about the enhancements that I'm doing. And I see I have 11 seconds, no, 9 seconds to do that. And so I thought, well, I would just tell you what my goals are and then tell you why what I'm doing is just going to be absolutely great And so I have only -8 seconds to tell you that, so I'll skip the goals and tell you what's great about it, that as I said, we are not adapting the grid and just sort of doing a normal thing to follow these, the details of this multi-fluid flow. And what we are doing instead is we're trying to do a very, very good job. And so I have a picture that looks like this. We're going to have, for these new flows, we have to be very careful about stuff that gets from one convection zone into the next. Because either way, if it either goes from the bottom one up or the top one down, there are violent repercussions. And so we're going to describe the behavior in each cell of 3 composite fluids, because otherwise, if we described each one of these isotopes with the same loving care that we have been doing so far, we'd just sort of go bankrupt, and we'd run out of memory and everything else. And so the idea is that we are going to use parabolas to describe in each of the 1D passes what the configuration looks like. And that sounds really pretty easy. It turns out that if you have a lot of these, the difficulty is how do you put all of the parabolas together in such a way that you can make a picture of the cell that is completely consistent, so that you cannot remove from the cell more than was in it, or you cannot take out a bit of these 3 different portions that all add up to more than should have gone out, and so on. And so I have in all of these other slides a discussion of how we're going to do it, and it's just absolutely marvelous, and I'm going to do it, and it's already coded, and I will even publish it. And if you have a question, you can ask about it, because there are 2 minutes and 30 seconds left. And so I'll stop. But I would like to just make one comment, and that is that Blue Waters has been just a wonderful experience for me. I think I said in here, and I don't know whether you had time to read it, that it changed my life, because it was in the first year, and well, maybe the first 2 years, it was a unique experience to be able to set up a really big run and have it happen in a reasonable time. All of these runs that we've done on Blue Waters, every single one, took less than 1 week to carry out. They used a lot of node hours, but then there are a lot of nodes. So every hour you could use many thousands of node hours. And so it was fun. And there was a lot of help from the other end. One of these where we did the second movie, I remember we had calculated for a day, which was all you could do, and then you had to give up the machine to somebody else. And I remember calling up Illinois and, hey, can we keep it? We're not done. And we sort of went day by day, when are we going to stop this run? Of course, it's using up lots and lots of time. But what was great was we could make that movie on Blue Waters, which we did, and we could stream the pictures to our locations. So you could see as it was going, kind of what it was doing, which helps you largely in whether you want to stop it or not. And so we let it go for 4 days, and it produced that simulation. And our previous experience with NSF Center Computing had been we would do one marvelous run every year, and it would take all year. I remember that we used the Pittsburgh Center, and they gave us 6 hours a week. Every week, all year, we did one run. What was great about this is that the runs they happened, and then they were over, and we could think about the next run. So that was a wonderful experience, and I want to thank all the people that made it possible.